Hello. Okay, so today I want to do the Mandelbrot Fractal. So these are the things that I always wanted to do. So these couple of days I've been looking at the basic theory behind the Mandelbrot Fractals, maybe like the background maths, and I was also looking at some YouTube videos describing. So this is actually a very nice video if you
It's
like it.
unstable. Sometimes it's
So describing
and if you do that, all you'll see is
concepts
sometimes it's stable
behind
like this.
the Mandelbrot fractal or Mandelbrot set. So the basic theory behind it is actually very simple. So I thought always, because these patterns are very amazing and they look complicated, but they arise from a very simple rule. So I'll just try to go just explain some basic idea behind the rule, and I will try to implement. So my final goal is trying to implement this Mandelbrot fractal and trying to zoom on it and have this effect, like zooming as much as I can and looking at the patterns. But before that, I want to, because this looks like a nice explanation, and I want to also do this animation where I want to see the Mandelbrot sets. So I'll describe the concepts and try to like implement this idea. So the Mandelbrot fractal, so fractal curve, is constructed basically from a very simple rule. So what we have a function. This function, it takes like a z, and so this function of z is the expression is d squared plus c. So this is basically the formula, and in this case both z and c are complex numbers, but let's assume for now they are just real numbers. So the idea behind the Mandelbrot fractal is you have a function f of z, and this is z squared. I'm trying to write it like this, plus c. So where z and c are complex numbers, but let's ignore the complex number for now. So what we are trying to do is we'll fit the function. So this is like an iteration or recursive iterative or recursive function. So what we are trying to planning to do is for some starting z. So usually in Mandelbrot sets we set z equal to 0 if it is a real number, but or z equals 0 plus 0 in the complex plane, and we'll try to find the value c. Okay, this is what we are trying to find, where the function f of z again, f of something like this. So we pass in the value of z, this formula, then we take this output and feed it again recursively, and we will be looking if this value either goes to infinity or if it stays bounded. That means, for example, one example I saw in the video, so this video is a great explanation actually, but let's assume for now that z and c are like real numbers. So f of z, for example, f of z is equal to z squared, let's call it z squared plus c. So for z equals 0, and let's say for z is equal to, for c equals minus 1, for example, if we compute on the first iteration, let's say on the first iteration f of z will be, so since 0 is 0 squared plus minus 1, so this will give us minus 1, this will give us 0 actually. So 0 squared is 0, plus minus 1 is minus 1. So then we'll take this output okay, and pass it again to this function. So for, let's say for example, for f of z, where c is equal to -1, how many times we compute this function, the value is always -1. But let's say for example for c is equal to 2, if you can see on the first iteration, so f of z will be 0 squared, which is 0, plus 2, which will be 2. Then now in the second iteration, f of z will be, okay, so we take this 2 and give it in the place of z, okay, so that means f of z will be, so now z is 2 plus 2 squared plus 2, so this will give us 4 plus 2, which is 6. Now in the third step, f of z will be, so 6 squared plus 2, because c will be constant, and so 6 squared is 36, 36 plus 2 is 38. And you can see the pattern. So for c is equal to 2, this function, when you call it iteratively, it goes to like infinity, so positive infinity. So this means for a value of c is equal to 2, this function, this iterative function, is not bounded. And for example, for a number like c is equal to -1, it is bounded because the value is always -1. So basically this is the rule. So what we are trying to find in the Mandelbrot set is, we'll take a number, so z is always constant, it is 0 on the first step, and for some arbitrary number c, we'll check if that number is bounded or if it is unbounded. So if it is bounded, so that means it's the number of, we count the number of iterations. Let's say in this case, after first iteration, that number is bounded to never, the value will never be greater than -1. So the number of iteration will be 0, for example, or 1. I'm sorry, 1. For this case, this will go to infinity. So we'll set some value like a maximum iteration number that we'll set. So we will count the number of iterations for that given value c, for the number to be either bounded or bounded by infinity, let's say. So this is for the one-dimensional case. So, but if you want to visualize it, okay, like for example, if you want to draw it, you need to have like an x and y dimension to visualize or convert it to a two-dimensional image. So that's why we consider the variables z and c as a complex number. So if we represent those as a complex number, then we can plot the x, the real value in the x-axis, and the imaginary value for the complex number on the y-axis. So that means we can draw it as an image and we can visualize it. So that's basically the overall idea. So I will go on with the code and try to implement. So my final goal is hopefully generating this and also trying to zoom and see all the patterns. So I will be implementing in C and Raylib. Let me check, is it recording? Yeah. So I'll be implementing the code in C and Raylib. I have already created a folder, and like usual, I have my make file. So if you want it, so let's start. First, let me create a C file, Mandelbrot.c. Okay, so let's include our required libraries. I just need some stdio, Raylib, and maths. I need a maths library and Raylib. And also one thing, since we'll be working on complex number. So we need the complex library for C. So complex numbers in C. So in C there is a header file where you can we can find a complex arithmetic. So it is, you need to import the complex.h header file. Where is it? Yeah. So if we import the complex, which is the standard library, then we can perform a complex arithmetic with it. So I need to include that into my library also. Include and steps copy and complex.h. Okay, so let's define some macros. Define the screen width. Let's make it a 800 by 800 square. Height. Okay, so int main void. Let's initialize our Raylib window. So it's a screen width by screen height, and let's call it Mandelbrot. So let's say target FPS, and let's make it 60 frames per second, and let's start our loop while window should close. Begin drawing and end drawing. Clear background. Let's make our background, let's make it black. Black. Then let's close our window. Okay, let's check if our code compiles. Make compiles, let's run it. Yeah, our window is working. Okay, so what's first? So let's go to our Mandelbrot. Okay, so there are some rules that we should consider. For example, so I have read here, so we treat the real and imaginary parts of the coordinate in the image coordinate at the x and y coordinates. And then, so now I'll go to it later, but now the coloring is very important. So like I said, I was talking about the number of iteration it took for the function to be bounded or go to infinity. So that is very important. That means we count the number of iteration, and that will be used to decide the coloring. Okay, so basically the color for these regions, it corresponds to the number of iterations it took for that pixel, for that specific pixel in the Mandelbrot set. If it is, let's say, it took 1,000 or 2 iterations for it to be bounded or unbounded. So that's very important. And the other thing, so the important thing is like, so we need a threshold. That means, so for a number C, and we perform this iteration like this, and how do we know that it's bounded or unbounded? So there is some decision threshold. That means if this function, we call this function iteratively, and its value crosses some threshold value, then that means that function is not bounded. Or after some iteration, let's say we limit the iteration to, let's say, 1,000 or 2,000. So if after 2,000 iteration, if the value of the iterative function does not cross this threshold, then that means that that number is bounded and it's part of the Mandelbrot set. Okay, so like a Mandelbrot Fractal is generated from Mandelbrot sets. So these Mandelbrot sets are like, these sets are set of numbers where those numbers value, if they are called, when they are fed to this function iteratively, their values will not cross the chosen threshold. But there is our threshold can be arbitrary, so we can set any threshold value. but what it says in the rule is that the threshold must be at least 2. Because in the Mandelbrot set, so this is, I think, the background maths here, -2 is the complex number with the largest magnitude within the set. So the threshold should be at least -2, but you can choose any arbitrary number greater than 2. So 2, not -2, 2. So that's the point. So for that, now when we are drawing in the image, let's run it again. So in our image coordinate, usually the top left corner is the origin point, 0, 0. But for this case, I want to represent the center point of our like square grid to be 0, 0. That's where I want the drawing to be performed here. This is where I want my visualization to start, not here. So what that means is that I need to have a mapping function. So I need to map the grid coordinates from the top left corner, starting from the top left corner, to the center coordinate that I want. So to visualize that, so let me first draw a line to make it easy. So my line starts at, I want to draw a horizontal line in the middle of the screen. So x will be 0, x1, and x2 will be at screen width. The height will be screen height over 2 and screen height over 2, and let's give it, let me give it a blue color for now, and let's visualize it. So make run our program. Oops, no. Screen is 0, draw line, x1, so x1, y1, x2, which is screen width, y2 is 2. Yeah. Okay, now let me draw a vertical line. So this is my horizontal. It's just a reference. I want to draw a graph, something like graph. So for my vertical, my x will start at screen width over 2. My y will be at screen height. No, it will start at 0. My x2 will be at screen width over 2. And my screen height will be at a screen height. So again, up. Yeah. So what I'm just drawing this, I will delete it later. I want to reference it. So what I want to do is, when I say, let's say for example, draw a circle at coordinate 0, 0. So in the grid coordinate 0, 0 is here on the top left corner. But I want it to be drawn at the center here. So that's the point. So that means I need to map the location from the grid coordinate to like image coordinate to my coordinate. So I will call it a Mandelbrot coordinate just for the sake. So that means I need to create a mapping function. So I give it a range of values and a minimum and maximum value and a value, and I want to transform that value to another range of minimum and maximum values. So for that, let me see what is called it, minimax normalization or future scale. Yeah, I have already. Yeah. So there is something called a future scaling. So anyone in machine learning or data science, they already know this minimax normalization. That means we have for any number x, we can convert its range from 0 to 1 by using this value. It's called minimax normalization. We have a value x, we subtract the minimum value that variable x can hold, and divided by the maximum value of x minus the minimum value of x. So this will convert the x. So let's say if x is a number between 0 and 10, and we want to change or map that number or normalize that number to be in the range between 0 and 1, we perform this minimax normalization. But then we can scale. That means we can scale that number to another range. If you want to convert to another range, then you can use this formula. That means, let's say we have, well, let's assume we have x. So if I have x, and if x was a number, oops. What is thickness here? It's very thick. So if x was a number between 0 and 10, and we want to change its range to be between numbers between, let's say, for example, -2 and 2, then we can perform this transformation here. So we have the a and b are the new ranges that we want to represent. So we'll take the minimax normalization. Then this is a scaling part. So we scale the normalized value and we shift it. So we scale it by the difference between the maximum and the minimum of the new set, and scale it by the minimum of the new set. This is called the minimax normalization. Then future scaling. So totally this is called a future scaling. So first, that means let's convert. Let's create a function. So I wanted to return a float, but let's make it a double, because then let's call this a map. So what this function does is it maps some value. This value is between min, let's call it inputs, okay, min inputs, and between max input. So the range is between min input and max input, and we want to map it between numbers min output and max output. This is what we want to map it, and what we want to do is we return. So we want to return this. So I will be copying exactly this formula. So a in our case is min output, so plus, so x minus, so x is our value here, value minus, so min x is min input, so times max output minus min input divided by max input minus min input. This is max output. Okay, so I give it a value, and I want it to map it between some range of numbers. Then I can use this. So with that, so I want to demonstrate what I'm trying to do. Let's say I have let's create a double x. Let's call this value at 0 and at 0. So if I came here and I draw a circle at x comma y, and let's make the radius, let's make it 20, or let's make it bigger, 40, and let's color it red. Let's make draw circle. See, now in the original grid coordinates is the center of the circle is here in the top left corner, but now I want to map it. Okay, so what I want to do is I want to create a new value. Let's call it double x value, and this is I want to map it. What I want to do map is x, and x is between 0, so the minimum value for the x is because x is on the x-axis. We are referring to the width, so the minimum value it can hold is 0, the maximum value it can hold is width, and I want to map it because now I'm drawing a grid, so and I want the starting 0, 0 coordinate to be on the center. That means to the left is minus width over 2. In our case, width is 800, so it would be minus 400, and to the right would be positive 400. So my new coordinate range is between minus 400 and positive 400. This is what I want to map. So let's copy, and for our y, so this will be y, this will be the height. Yeah, so now let me copy and draw another circle on this coordinate, and let's try it. Oops. Okay. Minimum input, maximum input. Let me check. Let's print our new values. X equal to x. F. Let me check. So x is minus 400 and plus 400. So it should not be minus. Let me check the formula here. So x mean a plus a value mean input times max input, mean input, max output, mean output. So let me check here. So I want to perform this. Okay. No. Mean output, max output. Okay. Let me pause this video and okay. So the mapping works, but I reverted the order. So that means now I want to plot on my new coordinate system 0, 0. So 0, 0 in my case. So let me delete all this. So I have a like coordinate something like this. So yeah, so in my image coordinate, this was the 0, 0. So this is the origin point in my image, but I want to map it here, which I want this to be my 0, 0. So I want this point to be 0, 0. So the idea is when I pass in 0, 0, I want it to be plotted on the image coordinate. So if we assume our image has a width of W and a height of H, and I want to tell my program to plot the image at coordinate 0, 0, and that coordinate is on my new coordinate system, and I need the program to transfer those 0, 0 into my image coordinate system. So in my image coordinate system, this point is width over 2, height over 2. So that's what the program is doing. So this is 0, 0 on my new coordinate system, new coordinate, and I want it to be mapped to map that coordinate to the image coordinate system. Image coordinate. So I pass in 0, 0, and I want the program to convert it to the image coordinate system. So that means my new on this 0, 0 on my image coordinate system will be found by mapping this x, which are the value between -4 and 4. So this is actually rather than hard coding it, I can say screen width over 2, screen width over 2, positive screen width here, minus screen height over 2, and screen height. So that's the value, okay, in my new coordinate system. That is the value. Then I want you to convert it to the image coordinate system, then plot it. So what we do is, for starter, so this the green image, so it's 0, 0. This one is on the image coordinate system, will be drawn at the top left corner. If I draw it without mapping it, but after mapping, this will be drawn at the center. So our red circle. So let's compile it. Let's yeah. So that's it. Let me come here. Zero, 0, positive screen should be screen. Sorry, screen height over 2. Yeah. So this one, with if I give it 0, 0 without mapping it, it will be drawn at the top left corner. But now, if I pass in 0, 0, and I want the image to be drawn here, but I want to communicate with this coordinate system, with a new coordinate system, but still the image will be drawn here. So what does that mean? That means if I want to draw, let's say, the image here, so this is in the negative x-axis, let's assume minus 100 or something like this, minus 100. Then from now on, I will just pass this value. So I want to draw it to coordinate system minus 100 on the x-axis. Oops. Then the image is drawn in the x-axis. So the green one is out of the screen bound. So that is the function of the mapping system. So I need the mapping because it's very important. Why is it important? Because in the Mandelbrot, when we are drawing Mandelbrot sets, we have a bound. Okay, so this Mandelbrot set, the values are bounded between -2 and 2. So that means we need to convert from the Mandelbrot grid to the image coordinate system for better visualization. Okay, So this is just for simplicity. So let me delete it now because I don't want it. Okay. Now let's start our Mandelbrot calculation, the recursive calculation. So for that, first I want to create two values, two complex values, z and c. So to create a complex number, we need to give it two type, the type, and we call it, I want to double, and we need to tell it that it's a complex number, so we add a complex and pass z. So I want z to be at 0 because z is always in the Mandelbrot set, z is 0. So in the complex plane, that is 0 plus 0 times I. That's how you define complex numbers in C. And I want also another value, C. And for now, let's say I want C to be, so like I said, C should be bounded between -2 and 2. So let's say C is -1 and plus 0.5. Okay. So this is the real part, this is the imaginary part of the complex number. So in C, we can find the real and the imaginary portions of the complex number or the components by using two functions. So we can use serial function and passing the complex number, and this will give us the real, it will return the real value of the complex number, and C image of the complex number, this will give us the complex value, and this will give us the real value or component. Okay, so if we have z and c, that means we can create a new function. Let's call it gates Mandelbrot or calculate the bound. I want so for each number I want to call it recursively, and function naming is always tricky. Let's call it get Mandelbrot set. Okay, let me call it this, and I want to pass in the complex z, double complex c, and the let's call it the iteration count. So the iteration count. Okay. So first what we do is we calculate, let's call it z prime, and this will be z squared b times z plus c. So I'm just implementing this function here, and so the idea behind it, we need to call this function iteratively. That means this is a recursive function now, so I need to call the Mandelbrot set and pass in z complex, and pass in c, and let's say I want this iter count, and I want to increment it. Okay, but now I need an exit condition for this recursive function. So the first exit condition is that we have a threshold, an arbitrary threshold. So after we call this function recursively, and we'll check the value of this one, the value of z, and if that value is greater than a threshold, then we can stop the recursion, okay? Or if it doesn't, then we will have to bound, because some values will go to infinity, like the positive 2 we took for as an example. So that means we could not calculate the operation infinitely, that we have to give it a bound. So let's define some macro constant. Let's call it max iteration. So the maximum iteration we will check, let's make it to 1000. So now our first condition is if the iteration count is greater than or equal to, it's usually, okay, max iteration, then we return or we exit out of this recursion function. So this is our first condition. The second condition is we check this, the magnitude of c. So in the complex.h, to find the magnitude of a complex number, there is a function called c absolute value. So it will give us c. So c abs of z prime. This will give us the magnitude, okay? The magnitude of the complex number. So the magnitude of the complex number is basically the square root of the real part squared plus the imaginary part squared. Okay, so this is what the function is doing internally, and we check if this value is greater than our threshold value. So like you said, our threshold value should be at least 2. Okay, for now let's make this 2, because it should be at least 2, or any number greater than 2. Then we return again. So this is our basic expression. Okay, so that means for a given number z, which is always 0, 0, so and for a Mandelbrot number that we want to check whether it is in the set or not, then we perform this iterative function. Okay, so that means, for example, here I can say get Mandelbrot set z, c, and iteration 0, then it will calculate. But this will be doing nothing. Now what I want to do is I want to initially visualize this animation. That means for each point on the Mandelbrot set, I want to see all the number of, because if, for example, it is bounded, I want to see for each iteration the value, the intermediate value. So that means this function should update some kind of array, and that array will hold basically so in the image the coordinates, okay, the value, the coordinates in the imaginary and real axis, or in our case the x and y axis. So what I want to do is I want to create an array, vector 2. So this array, let's call it points. So for each iteration, the maximum number of for this calculation, the maximum number of points or iteration we can hold is max iter. So that means it will be, we can guarantee that for a given point, when you call the function recursively, the maximum value, if the function goes to infinity, it's because we are stopping it at max iter. So that is, the value is here. So it's max iter here. So let's define an array, so points, and I want to, what I'm planning to do is, in this function I want to store the intermediate recursive values for C. So that means let me come here and I want to pass the array here. So since I'm passing the array by reference, let's call it point. It's a pointer. And so after doing that, what my plan is here. So I want these points, okay, is an array, and its either count value is a vector, okay, because then that vector holds the x, okay, dot x, and the dot y value. Now our x and y value are the real and the imaginary components of the basically z here. So that means I can here I can say serial of z and c image of z. So this will give us the x and y. Basically this will give us the x and y. But one thing we have to know is this value here, it always ranges between the number 0 and -2 in our case, because I'm bounding it between number 0 and -2. So again I have to map it, okay, map this value from the range -2 to 2 to the image coordinate. So we can do it here actually. What we can do is we can call in map. Okay, I'm mapping the real value, and this value is always between -2 and 2, and I want to map this value between 0 and the screen width. And again for this case I will map this value is between -2 and 2, and I want to map it between 0 and the screen height. Okay, so okay, yeah, okay, this seems okay. So okay, now that means I can pass the points array here. So this will populate the array with the intermediate values, which is a vector 2. So if it is a vector 2, that means I can plot it now. So let's create a void. So and let's call it draw Mandelbrot points. Okay, and I want to pass first the array, the points array, and also for now I can just loop through all the elements. Let's do it now. So for int I equals 0, 0 is less than max either plus I, and I want to draw a circle. So basically I want to draw a circle representing each point in the iteration. So let's call it draw circle. So the circle, so in the Raylib, where is Raylib? So in the Raylib function there is a draw circle. So there is circle V which takes in a vector value. So what you can do is update this vector V, and that is the points, because I have already transformed it here, so no need to do it here. I can say point I. Let's make the radius 3 for now, and let's make the color green for now. Just we'll play with the color later. So this is draw Mandelbrot. Now I have already point here, so let's come here and let's call draw Mandelbrot points. So let's check if it compiles. So there is an error. Yeah, okay, because yeah. Here we need to pass the point. Let's check. Okay, it compiles. Let's try to run it. Yeah, so these are supposedly the points. So now let's change this value to something. Let's make this one. Okay, yeah. Okay, but this is not fun. What I want to do is I want to use my cursor and I want to move it across the screen, and I want to visualize the Mandelbrot set numbers. So just like this, I want to see. So I want to replicate this. So this is my plan. Okay, so to do that, that means I don't want D here. Sorry. I want an event handler here. So let's say I want to use my left. So I want to click on my left mouse button and find the X and Y values on the grid, and I want to use them to construct C. So if I will say if mouse button is mouse button, I want it mouse button down, and so 0 0 is a left mouse button. If mouse button is down, so that means I want vector to mouse position. So mouse position can be gotten on Raylib using the get mouse position function. So this will give us the X and Y value. So this is on in image grid coordinates. Okay, so we need to convert this grid coordinate to our new coordinate. So our new coordinate is between -2 and 2. So to visualize it better, let me draw a circle here. So I need this circle for now. I can map it, or okay, yeah. So I need it to be in. I will be hard coding it now. Between 400, 400. The radius is 400. So because it's not good, but it will work for now. And I want like a white color. So okay. Draw circle line. Draw circle should be lines. Okay, so I'm just drawing this as a visualization guide. So hopefully what I'm trying to do is this coordinate in our new coordinate system is 0, 0. So this one is, for example, minus 2, 0. This is 0, positive 2, and this is 0, positive 2. This is 0, negative 2. This is 2, 0. So this is our bound. Okay, so this is our Mandelbrot bound. So basically what the theory behind the Mandelbrot set says, so any number inside, okay, any number inside this Mandelbrot set, it's when they perform the calculation recursively using z squared plus c, its value is bounded, so it will never go to infinity. That's a theory. So we will be testing it using our visualization. Okay. So here now let's see uncommon bit. So I have my mouse position. Okay. So now let's call it double x. This is my new coordinate. Mouse position. Let's call it mouse pose. My new mouse position on the Mandelbrot grid is I want to map it. So to found, I want to map mouse position. Mouse position is between 0 and the screen width. It's between 0 and screen width, and I want to map it between negative 2 and 2. Okay. So mouse pose. And call it x, this is y, this is mouse pose dot x because it's a vector 2 dot y. So this is between the screen height. Okay, then now I want to take this, come here, oops, J, paste it here. Now my complex value c will be mouse pose x, my new position, times mouse pose my. Then text is here, go back 70 here and paste it. So now I want to call this function only when the button is pressed, and I want to track the mouse button coordinate and use that as the value of c and perform the Mandelbrot calculation, then draw the points. So this is basically what I want to do. So let's try it, and hopefully it compiles. Okay. Get mouse position. Oops, okay, this is position. Get mouse position. I think that one there. If mouse button down. Let me check the Raylib documentation. Mouse button press, mouse button down. Oh, sorry, this is mouse button down. Let me check. Okay, mouse pose. Mouse pose. I think now it's okay. Yeah, let's try. Okay, yeah, so this is basically what I want to do. So this is I want to replicate this. So now these are the points. So let's say, for example, for this value c, but there is some problem that I don't want it to draw. I want it to clear. this array and draw Mandelbrot port. Okay, so that means I need to I need some way to know the current iteration count. So let's pass in iter count equals 0, and also needs to be int iter count. I don't want it to be okay. Okay, and here I want this to pass by reference. Okay, this is not good, but it means this would be the value of iter count, and this will be the value of iter count plus 1. So the value of iter count plus 1, things like this. Value of the value of iter count plus 1 plus iter count. Okay, so I have iter count is equal to 0. Okay, I'm going to count and I want to pass get Mandelbrot sets. And write it. Okay, and let's pass it by reference. Pass item count. So anytime this is written, I want to set it to 0. Okay, let's try points item count. Points like the value of item count. Let's see. No. Okay. Enter count. I think I ruined it. Let's go back. Go back. Yeah. And I should just bring this here. Let me try. Integer count is not an integer. to where's draw? Should be max item. Points, draw points. Okay. Again, yeah. I shouldn't have touched it. This another points. Line 28. These points. This. Yeah, this is what I want to do. Okay, so now this means what we are trying to visualize, okay, in this case. So for any number, if you can see inside this circle here, these are the values for the recursion. Okay, and you can see it is always bounded, but when we go outside of the circle, I'm not even visualizing here. So here for numbers inside here is bounded. But there is still some problem with my code, with the way I am huge. I think I'm not updating it correctly. Okay. So I get my points. I update the points there. Draw the points. I shouldn't draw all the points. There is something. Let me check. Let me pause the video. Okay, so I just fixed some stuff. That means now yeah. Okay, so these are the values. So for some value C, these are the iterated values. Okay, so that means inside here they are bounded. Okay, and when you go outside, it just goes to infinity. That's basically it. So let's try to display the numbers I want to visualize. So I come here. I want to select a function called draw text. So I want to draw it at mouse. So at mouse position, at mouse pose. Okay. But before that, I want format text. Is it? Let me check. Format text format. Is it text format? Yeah, text format. And is there a draw text v? Draw text image? No. Draw text. So there is draw text colon scar in pose xy. Okay. So I can say format text. In my format text, I want to say C equals, is it a floating point plus another floating point I, and that is mouse. These are the mouse pose mx and mouse pose my. position is mouse pose X, mouse pose X, mouse pose Y, and the other parameter is color. So let's make the color to white. Let's check if it's working. Okay, it's I think text format text format. Draw text objects. No V. Okay. Let's make draw text format. Format text. Mouse draw text format. Accepted 5, expected 5, and half 4. So I need the text info, font size and color. Okay, so there is font size parameter here. Let's set the font size. Let's see. Okay, let's check now. Yeah. Okay, so let's make the font bigger. Let's set it to 8. Is enough. Let's clean. Yeah, the font is still small. What's happening? Okay, let's make it 20. I'm not sure why the font is small. Yeah, okay, this is what I want to know. So this position, so the value is, it tells us the X and the Y value here. Okay, so the Y value in our coordinate is the imaginary part of the complex number. So like as you can see, so for some values it's like it's a spiral, that means bounded. Okay, and like for some values inside here also, this number goes to infinity. So the theory says any number within this range is bounded. Okay, these are the Mandelbrot sets. So any like infinitely small real numbers inside here that are represented by the complex value are bounded. That means they will go on forever to let's say to infinity. So the bounded notion is that, like for example, for some value here, let's say for this value, so when you call it iteratively, even after some infinite number of calls, its value will never exceed positive 2. Okay, but for some values, like I think this is the value, let's say this one. See, so after some iterations, its value escapes. Its value is greater than, the magnitude is greater than positive 2. So this point is not part of the Mandelbrot set. So I want to also visualize the number of iterations here. So I just want to copy this, paste it here, but now let's call it iteration for it to bound. It's an int, and it is the iteration count. Okay. The iteration count, and I want to put it on the top left corner. So this is for some visualization. So I want it to be at around, let's call it 600, 50. Draw. And also mouse position X. Yeah, okay. Okay. Yeah. So like no, it's not updating. Yeah, no. So because iter count is always 0, I want it to be here, and also mouse position X. Let's try here. Okay. It's not correct. Okay. Let's put here. Draw text. Get Mandelbrot set. Let's print this after the calculation. And let me try. Yeah, okay. So this is the iteration count. Say, for example, for this value, so even after, because this is 1000 is the maximum iteration, so even after 1000 iterations, its value is always bounded within, like it will never escape +2. But for this, for example, for this value, for value of c at minus 0.36 plus 0.71 in the imaginary axis, after 8 iterations, its value escapes. It's greater than the bound, that is +2 or -2. So this point is not part of the Mandelbrot set. Okay, but there are some points. For example, let's check here. This one escapes. This one escapes. Yeah, this point's part of the Mandelbrot set. I think yeah. This is also part of the Mandelbrot set. Okay. So these are not obviously part of the Mandelbrot set, because after like let's say 8 iterations it escapes. Okay, so yeah, so this is the visualization that I want to do. Okay, so far it's good. It's like nice. So for some points, right here. So we can add a line to create this pattern. I think it looks even much prettier. Let's try it here on the draw. So I was drawing a circle, but I can also draw a line. So I can draw a line. So what I can do is I can draw line V. Is it draw line V? Let me check. Draw line V. Draw line V. So with start position and end position, so I can pass. So I can draw a line. So since it is equal to iteration count, I can modify this thing. Okay, so what I can do is draw line V from points I to points I plus 1. Okay, but I think it will be array out of bound exception in this case. 0. Okay, let me just write. Let me give it a red color. Let me check. But I don't think it's correct. But yeah, it is. No, it is not actually kind of correct. So 0.0 is 0,0. So if you can see in the video, so we're starting from I equal 0. Okay, so that's the issue, because I'm not adding this one here. Okay, I'm always starting from the okay. Okay, what I can do is paste here. It's not efficient, but okay, it will do for now. So I can here something like this, and from points I to I plus 1. This will, but it is not efficient, but it kind of works. Now yeah, it is kind of similar. Let's say, for example, yeah, I can check with the video here. Yeah, it's kind of similar, but it's very crowded. I don't like it. So let's just stick only with the points, drawing with the points, because we can play with the points. Now we can play with the color value. So for example, for now it's only color is green, but what you can do, we can make the color be dependent on the iteration count. Okay, so for example, you can set the RGB. So there is the R value could be some like, you can make it like a Fibonacci sequence, I guess. So you can do 255. The G could be 3 times item count. 0255. The blue. RGB. So let's make the blue kind of lighter, and the alpha channel here, and this could be C. Okay. Now let's yeah, so we can play with the color. So okay, so for some values it's all green, but it's very dark. Anyways, for now I just want to stick some solid color. Just I want to say 155 128 50. I don't know what color it is, but let's stick with it. Okay, you can play with the color, it doesn't matter, but we got the point. So what this visualization tells us is if it is bounded, the iteration value, that means this the exact that point is part of the set. If not, then it's not part of the set. So this the color gradient point is what we'll be playing later. So that is what creates the Mandelbrot set. So for now I'm calculating the Mandelbrot sets for a given number like manually. But now what I want to do is I want to calculate for all points here on the grid, for all pixels basically. So once we have this foundation, then it's very easy. So what we can do is we can create a new function. So that function calculates it does the same thing, but now it will not be like an iterative function. So the function will return the iteration count, okay? The iteration count for a given point, and we will use that point to like color, or like to color and give it based on its number of iteration. We need to give it some form of color. That's how I can explain it. So let me write it and you can understand. So what I want to do is I want a function that will return the number of iteration it took for a point to be unbounded or go to infinity. So that function, let's call it generates Mandelbrot. I don't know this. Let's call it get iteration count. It's hard naming functions here. So this function will take so what this function takes is it's like exactly same. It will take these two values here, but now I can only use this value because z is always constant. It's always 0. That means I can use double complex C, okay? So I can pass this value here, and I think this is enough. Then after that, I can define double complex Z. I can define it here 0.0 plus 0.0 times I. Now let me define a value, call it iter count, and so we have two type of values. Some are bounded and some are unbounded, or they go to infinity. So some go to infinity after some value, and some go to infinity so they will go to infinity after an infinite time number of iterations. So let's say for those values, okay, for those values that will go on forever. So but we cannot go forever. We have already defined a max iter value. We'll give them a default value of -1. So this is just like, so if the iteration count goes beyond max iter, this is the whole point. Okay, now for int r equals 0, r is less than max iter, plus I. Now we will compute, okay, this, so exactly the same. So I'll be computing this, so this, and come here, and I want to set now z equals to z, and I will check. So same again, I will check this value, go to here, paste it here. So now if that value, the magnitude is greater than 2, I want to return how much step it take to go beyond that bound. Okay, so I want to return I. Else, then if the loop that is finishes, okay, goes to max iter, that means that number, okay, that means that number I need to return iter count. So iter count will be -1 if that function, when you call it recursively, it goes to infinity, or if it goes to infinity after some number of iterations, then we'll return that iteration value. Okay, so this is our get iteration count function. There we need a new function now. Let's call it void generate Mandelbrot fractal. Let's call it generate Mandelbrot fractal. Let's call it Mandelbrot fractal. Okay, so in generate Mandelbrot fractal, we need now so we'll be coloring the pixels. That means I need the pixel information, the color. Let's call it the pixels. I need the pixel. I think this is enough for now. Okay, then I will go for int I equal 0 for each pixels equal 0, I is less than screen width I, and for int j equal 0, j is less than the screen height. Okay, so this is still the image coordinate. Now for each pixel, I want to first find its value in the Mandelbrot coordinate, and use that value to calculate the iteration count. So what I want to do is, so I want to say my float image, let's call it x and y. Okay. So this is in the Mandelbrot coordinate. Okay, if I want to map, so the x is the I value, so it is between 0 and the screen width, and I want to map it between -2 and 2. The y on the new coordinate is the j, and this is between the height. Okay, then now I want to create a float complex c, which is xm plus xm times I, and this is double. Okay, now then I can say int iter count equals get iteration count of c. Okay, so I have get iteration count of C. Now based on the iteration count, I would need to give a color to the pixel here, to the pixel located in the location I, j on the image coordinate. So what we can do is by default, what is it? So where is my, so by default for so this black region is values within the set. So that means anything within the set means, so what we defined for number within the set is if its value is so if its value is actually -1, yeah, if its value is -1, then it's part of the set, but it will go to, that means it's bounded. And if let's say if its value is 0, that means after the first iteration it has passed the bound. So what I can say is for so let me come here, first define a color C, and I say first if the iteration count equals -1, that means this value is part of the set, the Mandelbrot set. So C will be 0, 0, 0, 255. That means this is black region. Else if it's not -1, okay, that means that part, that corresponding pixel is not part of the set, then we can color it based on the number of iteration it took to go beyond the bound. So for that we can use anything, like let me, but I have found something that works. So let me color, and I think it should be color. I need to pass it to color. Color. So I use the for the RGB some ratio, like the some constant, maybe part of the Fibonacci series works better, I don't know, but let's say 8. I need to cast it to int first. No, sorry. To it's not int, it's unsigned int. I use it unsigned, yeah, unsigned int, because currently unsigned int. I can say 8 times the iteration count, and let's modulo it to 55, range it. So this is R, dot R, and I can say dot blue could be here. R equals do B is the unsigned int 5 times, so it's just like a Fibonacci series. Iter count modulo 255, and for RGB, for the green, I can say it's unsigned int 3 times iter count modulo 255. Then the alpha channel is just 255. Okay, so that is the color. Now we need to give that pixel this particular color. So what you want to do is I times the screen width plus j is the color. Okay. Okay, this seems to work. Okay, now after that, let's create a new function that draws those pixels. So let's come here. I think okay. Draw fractal. Let's call it draw Mandelbrot Fractal. Again, take the color pixels. Let me copy this. Okay. Then I need to say there is a function called draw pixels. Okay. So I need to draw pixels. Before that, this where is it? This R I comma j in the script coordinates. Okay, yeah. Draw pixels. So let me check the documentation. Draw pixels. So there, draw pixels. So draw pixel in position y, in position x. So draw pixel at I comma j, and its color value, the third parameter color value, its pixels I times the screen width plus, I think this is basically it. Okay, so now let's try it. Get Mandelbrot Fractal, the pixels. Okay, so that means I need to create a new array. So it's color is type pixels. I want to allocate it dynamically here, this one. So it's a screen, so this is the number of pixels and the size of color. Okay, then I want to say generate Mandelbrot Fractal for these pixels. After that, I want to draw it here. Maybe draw Mandelbrot Fractal. I want to pass in pixels. So I want to generate it there and draw it here. So we comment this for now. First, let's check if the code compiles. So there are some errors. Draw pixels. Is it not draw pixel? Draw pixel, not pixels. So it's draw pixel. Void generate. Function definition is not allowed here. Void generate. Void generate line. It's line 52. I'm not sure what is it saying. Let me try. Generate. Function definition is not allowed here. I think I've done something. So window should close. if okay this function okay, let's fix this if else this okay. I think this is the case. Oh, oops. What is happening? This definition of C was different. C. Okay, so this should be, let's call it okay, moment of truth. Oops. Okay, so there's some bug here. So let's see. So generate Mandelbrot set. What is it? Get the iteration count. Iteration count is 81 to max iteration. Calculate D. Set C is equal to if absolute value of C is 2. Okay, I think return iteration is working. So the problem seems to be here for I times the screen width plus J. Okay, so map xm is the mapping to I and J. It's I times screen width. I want to map it here. Okay. Pixels I equals I times screen width plus J. Okay. Okay, let me pause the video. Okay, so I think the bug seems to be here. This should be why. So let me check. Yeah. Okay, so we got our Mandelbrot fractal. Okay, this seems to be nice. It's working nice. So this is already accomplished my goal. So today I wanted to visualize this point here, to this animation. So this is great video if you want to understand the overall maths and theory behind Mandelbrot's. And I wanted to generate this. Before it looks like something complicated, but all this arises from a very simple rule, just a very simple rule of applying this function on a set of complex numbers recursively. Now, my next goal is, I'm sure it will not be this smooth, but I want to like zoom in into the set, because if you go to a smaller number, like a number range, and perform the calculation again, so you'll find new patterns. So I want to implement some form of like zoom operation, but zooming means in this case, yeah. So on this case, we are calculating the sets for numbers, complex number between bounded between -2 and 2. So zooming means like for some zoom factor. So if I want to, let's say, zoom it twice, okay, that means I want to calculate between like 0.5 and -0.5, like halving that number, if I am clear with that. So let me let me try to implement it, and I think you'll get it. So until now I was like bounding, hard coding the bound here for the number between -2 and 2. But when I want to try, that means I want to change the bound. So I want to go smaller bound. Let's say if I would zoom in to a factor of 2, okay, that means I am like looking between numbers between -0.5 and +0.5. And if I even like zoom in a lot of times, that you might look between numbers -0.00 something. And so the smaller the range you look, that means you are zooming into the fractal. But I think that will be limited by the precision you have. So that's why I was using double here. So for that, let's create some like global variables to hold this factors, okay, the Mandelbrot minimum and maximum bounds. So let's create a I mean, it should be, because this should be a double yeah, double so let's divide it for the x and y. X x mean let's go to Mandelbrot min for the x. Let's give this -2 for now. Mean for the y, same. Then we'll copy. Now this will be max for x, will be 2. Max for the y axis is 2. Then, so wherever I hard coded this value, so this will be Mandelbrot min x. Yeah, for the x, so this will be Mandelbrot max x. This one will be Mandelbrot min y, and this will be Mandelbrot max y. Okay, so we go everywhere. So that's the magnitude. Here this is again for the x, so it should be Mandelbrot min x, Mandelbrot max x, x and Mandelbrot max x. Mandelbrot min y and Mandelbrot max y. Let's step first. If it works, that works. We should have the same. Yeah. Now let's create a new function. And let's create here. Let's call it void zoom. Call it Mandelbrot. So the zoom Mandelbrot. So to zoom in, we need the xy, where to zoom, and how much we want to zoom. Okay, so that means we need the double. Let's call it the mouse x, because this will be the on the grid coordinate. Double mouse y and double the doesn't float is thick enough. Zoom, I want to say zoom factor. So how much we want to zoom. Okay, so then first I need to find the new range. Okay, so the new range means so I have mouse x, mouse y. Okay, so I think this needs a bit of thinking. Okay. Okay. So first, this mouse x and mouse y are on the image coordinate, so we need to map them to our new coordinates, Mandelbrot coordinate. So let's say first let's find double mouse x. Let's call it the m to denote that it is the Mandelbrot coordinate, and I want to map it. So this is initially between 0 and the screen width, and I want to map it now between since x it is the Mandelbrot min x, Mandelbrot max x, and do the same for the y. So it was to screen height and screen height, the min y and the max y. Okay, now after we do that, now we need to find based on the zoom factor, we need to find the new range. So the previous range, okay, the range, the bound we are looking, it was between -2 and +2. That means we are looking at numbers, a range of 4, if you are just counting with 1. Okay, so that means what I want, my idea is I have double, let's call it x range. This is the new range. I don't need to say that, but so what I want to do is like, so I have the Mandelbrot max, what is it, max x minus the Mandelbrot min x. So this will be +2 minus -2, which is +4. This was my previous range. I was looking at if I'm counting with 1, I was looking at 4 numbers, so the range of 4 numbers. Now I want to look if I am zooming in or zooming out. Like so, this factor, if it is a number greater than 0, that means I am looking out. Okay, zooming out. If I'm looking, my zoom factor is, for example, let's say 0.5. That means I will be looking, previously I was looking between numbers between -1 and 1. Now I'll be looking between numbers. No, it was previously -2 and +2. Now if it is a factor of 0.5, that I'll be halving it. So I'll be looking between numbers -1 and 1. So that is this zoom factor will give us the new range. Okay, to give us the new range. So this is for the x, and we do that for the y also. Y. Okay, that will give us our new range. Then now, after doing that, so we need to update our these bounds. Since we zoomed in, now we need to also update our new bound. So we will be updating our new bounds based on the range. Okay, so what we do is for Mandelbrot min x. Now min x will be, so previously it was 2. Let's say if we have it, then it will be again, I think so it will be some parameter of this x. So we need to find so it was between -1 and 1. Now it's our cursor, so where our cursor is, and minus the x range. So the minimum will be x minus the range divided by 2. Yeah, I think it's our mouse x, our new mouse x, minus our x range divided by 2, because we want the cursor position to be the new center of our zoomed in grid. So for the y, this will be y, this will be like this, and Mandelbrot max, max x will be mouse xm. Now it will be plus range over 2. Max y, this will be again. So this is where we update it. Okay, so we'll be updating these new bounds. Now to zoom in, we can so that means whenever we zoom, we need to call this function again. This will make it very slow. I don't think it will be like, I'm not sure it will be this smooth. I don't know how they did it. Maybe they did it, they use like shader or something like that, maybe on the GPU, but that means every time I zoom I have to calculate this, and it will be slow. But let's try implementing it. And I want to bind the zoom function to some key. Okay, let's say if I press the Z key, then it will zoom in where the mouse cursor is. Okay, so if is a key pressed, okay, for zooming in and zooming out, let's say for zooming in, we say key, the up and down key, yeah, let's make it the up, key down, key up, let's make it key up. If key, so the up arrow key is pressed, then first I need to get the vector to the mouse position, because that is a parameter that will be passed, is equal to get mouse position. I need to get the mouse position, float the zoom factor, since I am zooming in. So zooming in this case means my zoom factor, let's say I will zooming 2 times every time I click. So my zoom factor will be 0.5. Then I will call zoom Mandelbrot. I can simplify this one. So I can, yeah, okay, no problem. I can pass the, so that's not double, but I can pass mouse position dot x, mouse position dot y, and the zoom factor. So after that, that means every time I did that, I have to call this function. So this would be very slow, but that's the only thing I can do. I don't know how to make it like fast and smooth, but we'll see. So this key down will be, now we'll be zooming out. So that means so it's not I'm just doubling in and out. So in this case, get mouse position. So this is set. Yeah, I think this will work. Let me try. Let's clear. Let's compile first. Is it so? Do you have some errors at line 92? Where did the error? So map screen. Oh, map mouse x, map mouse y. Okay, let's try. Nice range. Where is the range? It's 999. Oh, this is small. Okay, it compiles. Let's try. Okay, now let's press the up arrow key. Oh yeah, it works, but there is some kind of like okay, yeah, it's not zooming it, it's like flattening, making it flat. So there is some mistake here. Max x, max y, mean x, xm has x range, mean y. Max x is max x range. Oh, this, yeah, this is not correct. I hope this is the code, because it was easy to find. So now let's zoom in. Oh yeah, it works. So let's come here. Let's come here. Oh yeah. Nice. This is always satisfying. But I can't zoom in forever because like you see, this is the limit I can zoom in. I don't know why, but I think it's due to maybe the precision. I'm not sure. Let's zoom out. So zoom in and zoom out works. Yeah, it works. Okay, it works fine, but I wonder why the resolution is like very limited. I'm not sure. Is it here? Maybe the zoom factor. Shall I include the precision? I'm not sure what to do. I don't know why. Most excellent. Is it because the precision? It's two. Oh, I think this is a cause. It should be double maybe. Let's see. Because I think it's the cause is this the precision. I'm sure it's the precision. So even this one, it should be double. Because I think float is 32 bits in my machine. So there is a limit of like a resolution limit I could go. So let's, is there another float? Yeah, okay, I don't know, but this should be double. No, okay. Is there another float? Okay. Let's try again. Oops, sorry. Let's zoom in here. Zoom here. Oh, zoom in. Okay. Zoom in, zoom in, zoom in, zoom in. I want to see how much deeper I can go without losing the resolution. Maybe it would be better to count, maybe. Okay, this seems better. I think so. The issue was like the type. Okay, like this is good. Okay. So this always amazes me. Now, the deeper you go, you still find this pattern again. Then, like you could go in, zoom in, and this pattern here, this will go on forever. So the further you zoom, this pattern will be repeated infinitely. So they say in like these Mandelbrot fractals, they have like an infinite perimeter. Like you can zoom in forever, but this pattern will be repeated here. So I think I have zoomed in more than 10 times now. A factor of 10 or 20, I'm not sure. So the resolution is still nice. So this is the effect of double. Okay. But like I said, it's very slow. Zoom in here. Okay. Oh, it's getting slower and slower. Let's zoom in here. Now it's like the resolution is becoming poorer now. Yeah, you can see individual pixels. So I think this is the limit of my machine. Maybe you need 128 bits PC or something like this, or maybe there is some optimization, I don't know. So now just let's zoom out. Oh, it's very slow though. Zoom out. 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 Oh my god, so slow. out. Yeah, now there is a point where like it becomes faster. I don't know why. So the deeper you go, the slower the calculation is. But now like it's quicker now. But it's very nice, like it's very pretty in the patterns. Yeah. So this is the Mandelbrot site. And one thing I want to do is like, because I need to this one, I want to see it, but that means where is my draw pixels? I need to make this draw rectangle icon 1 and width, just 1 pixel width. Okay, because where is it? Points. Is it? Okay. I hope I didn't delete it. Next one, is it 1? Next iteration count. Draw rectangle icon. Is mouse button down. Yeah, let's check. So, come on. Yeah, this is what I want to do, because now we can demonstrate like so. For this black region here, all the black regions are where the values are bounded. So you can see, so whenever my cursor moves around inside this black region, even here, those numbers, even they are disconnected, but they are bounded somewhere. But in the edges, they are unbounded here, if you can see. The edges, they are unbounded. Inside these black regions, they are bounded. So here, they are bounded. And there is some cool patterns that happens. For example, when you go to this region, so the points are inside like this, for example, here. So this is like a cool visualization, I guess. So this was a nice like project. I always wanted to do the Mandelbrot visualization. Hopefully maybe in the future. I'm not yet like a good graphics programmer. Maybe I can make the zooming effect faster, maybe smoother, and create a cool animation like this. But for now, this was a very fun project for me, and I hope you like it. So I always thought they were like complicated, but Mandelbrot sets are like very cool, and their concepts is actually very easy. So hopefully you enjoyed the video, and we'll meet next time with another content. Bye.